In 18 days, you're going to get the closest look we've ever had at an interstellar visitor. And in this video, I'm going to give you 3 things to watch for. 3 anomalies you can actually track, so you'll know whether 3I Atlas is acting like a normal comet or like something that shouldn't exist. Because right now, the official story is just another comet. But the data, especially the amateur data, is quietly building a very different picture. And here's the part that makes this urgent. The window to catch the best evidence is short. The geometry is about to swing in our favor. And then, it's gone. If you want to stay on top of every update while this plays out, you can subscribe anytime. Because the next wave of observations could either calm the whole story down or make it way harder to ignore. All right, let's set the stage. Official channels keep writing off 3I Atlas as a normal comet. But a global network of amateur astronomers has been capturing imagery and astrometry that's exposing things the official summaries won't touch directly. A sunward structure stretching roughly 1 million kilometers, physics that doesn't like the math, and a stack of anomalies that even revised trajectory models can't fully explain away. And if what's driving this object isn't natural, we're going to have to rethink what's cruising through our solar system. So, let's walk through what's actually happening. First, the timeline that matters. On July 21, 2025, the Hubble Space Telescope captured its first clear image of 3I Atlas from nearly 4 astronomical units away. That shot became the reference point. But now, 3I Atlas is approaching its closest point to Earth, less than half that distance. And here's your first anchor number. Don't lose it. The minimum approach brings 3I Atlas more than twice as close as during the Hubble image. It shrinks the gap from about 3.8 astronomical units down to roughly 1.8 astronomical units. That difference is not subtle. At this range, even modest scopes can resolve finer detail in the coma and tail. And Hubble plus the James Webb Space Telescope are expected to deliver images and spectra at resolutions we've never had for an interstellar visitor. Now here's the first open loop. When an object gets twice as close, it doesn't just look prettier, it becomes harder to hide behind maybe. It becomes measurable. So if something weird is going on, this is the moment the sky starts forcing answers. That's why scheduling time on these telescopes has turned into a global effort. Observation windows are tight. The object moves rapidly across the sky. Every hour counts. JWST plans to capture infrared and visible data, targeting not just the main nucleus, but faint extended structures that have drawn so much attention. Ground-based observatories like the Very Large Telescope and Gemini South are coordinating with space-based assets, trying to build a time series dataset as 3I Atlas sweeps through closest approach. And what makes this opportunity unique isn't only the proximity, it's the timing. Post-perihelion, when a typical comet would fade and quiet down, is when 3I Atlas is most accessible to Earth-based observers, and the geometry means we'll catch it from a new angle. That can reveal features that were hidden or blended in earlier images. And here's the second open loop. Some of the biggest discoveries so far haven't come from the world's biggest telescopes. They've come from amateurs, because amateurs can work nightly, share raw data instantly, and publish an audit trail the moment they see something. And that's exactly what's been happening, while the world's largest telescopes coordinate schedules. The most revealing imagery has often come from a global network of dedicated amateur astronomers, capturing extremely detailed views in the post-perihelion phase. These aren't casual snapshots. A lot of these observers are using setups that rival small professional rigs, large aperture reflectors cooled CCD/CMOS cameras, precise tracking mounts. Their frames are sharp, their plate solved against the Gaia star catalog, locking the object's position down to fractions of an arc second. And that matters because it means these measurements aren't just impressive, they're verifiable. One standout contributor is Michael Yeager, who recovered 3I Atlas on November 8, 2025, just days after perihelion. His images, calibrated with Gaia WCS and submitted in FITS format, provided the first high-confidence astrometric points after the solar passage. Other amateurs across Europe, North America, and Asia have coordinated nightly campaigns, sharing raw data, cross-checking measurements, and submitting results to the Minor Planet Center. And in multiple cases, amateur images revealed faint structures in the coma and tail days before they appeared in professional releases. Each observation comes with an audit trail, UTC timestamps, exposure details, plate-solved astrometry. That level of rigor means the community measurements can be trusted and checked, not just admired. Now, let's get to the feature that kicked off a lot of this tension, because this is where the physics starts to feel like it's slipping. A structure pointing toward the sun, a sunward plume, stretching on the order of 1 million kilometers, a coherent, collimated feature that points into the solar wind. This isn't a tail streaming away, which is normal. This is the opposite direction, and that's where the discomfort begins. At the distance of 3I Atlas, the solar wind barrels through space at around 400 kilometers per second. That's roughly 1,000 times faster than typical comet gas jets, which rarely exceed approximately 400 meters per second. Picture trying to walk into a hurricane moving at 5,000 kilometers per hour. Any dust or gas ejected from the surface should get swept back instantly, forming a tail streaming away from the sun. Yet for weeks, images have shown a jet not only resisting that onslaught, but holding a coherent, collimated shape, pointing straight into it. Physics says this shouldn't be possible without extraordinary force, because the ram pressure from the solar wind doesn't just push against the plume. It scales with velocity squared. It hits hard. And for that sunward structure to survive, the outflowing material would need to be at least 1 million times denser than the solar wind itself. And here's where the math gets nasty. That density implies a mass loss rate that is hard to reconcile with an intact nucleus. Even conservative estimates put the loss at about 200 metric tons per second for every 300,000 kilometers of exposed structure. But the visible structure is larger than that, and it persists for weeks. Add up October and November, and the total mass loss climbs into the billions of tons. Avi Loeb's team, using generous assumptions, puts the minimum nucleus mass around 33 billion tons. Losing several billion tons in around 6 weeks means 3I Atlas has shed at least 10% of its total mass, possibly more if smaller nucleus estimates are used. For a standard comet, that kind of hemorrhaging usually leads to catastrophic breakup, fragmentation, disintegration. Something gives, but it doesn't. The nucleus remains intact. The sunward structure persists, and 3I Atlas keeps defying basic comet behavior. So here's the third open loop. If the plume is real, and if the mass loss budget is even remotely close, why isn't the object shattered? What closes the budget? That question collides with another one, the trajectory. Because non-gravitational acceleration, NGA, is supposed to be the calling card of an active comet. Jets push the nucleus off its predicted gravitational path. That's normal. But the timeline for 3I Atlas doesn't fit the script. Throughout the summer of 2025, the object tracked a perfect gravitational arc. No sign of outgassing and no deviation. Just a clean, inert trajectory. Then around perihelion on October 29th, the numbers changed. Suddenly, JPL Horizons reported an NGA near 1.66 times 10 to the -6th astronomical units per day squared. That value didn't last. As more astrometry poured in, Horizons dropped it to about 4 times 10 to the -7th astronomical units per day squared. A few weeks later, it fell again, landing just under 7 times 10 to the -8 astronomical units per day squared. Each revision shaved the anomaly down, nudging the projected path closer to gravity only. These aren't trivial adjustments. At the original value, the implied force would require the object to shed more than 10% of its mass in weeks, on top of the billions of tons implied by the sunward structure. And here's why the budget hurts. Comet gas moves at about 0.4 kilometers per second. Low exhaust velocity means high propellant cost. That's not an opinion. That's the Tsiolkovsky rocket equation. The same logic behind every rocket launch on Earth. If your exhaust is slow, you need to throw away a lot of mass to get a little acceleration. So if the acceleration is real and the exhaust is comet-like, the nucleus should be vanishing before our eyes. Now compare that to engineered propulsion. Chemical rockets eject mass at about 4.5 kilometers per second, over 10 times faster than comet gas. Ion thrusters can reach 30 kilometers per second or more. For the same change in speed, chemical propulsion uses about 1/10 the mass. Ion propulsion uses a fraction of a percent. The numbers close elegantly. Now let me be clear. I'm not saying this proves it's artificial. What I'm saying is, when you do the bookkeeping, low exhaust velocity makes the object hard to keep intact. High exhaust velocity makes the budget easier. And that's why Avi Loeb frames it the way he does. If you want to move an object efficiently through space, you use the highest exhaust velocity you can manage. Nature doesn't do that with comets. Technology does. So here's the open loop you should be feeling right now. Is 3i Atlas following a comet script or a propulsion script? And if not, what is it doing that we're mislabeling? Now we move from the numbers to the jets, because jets have their own fingerprint. And this is another place where 3i Atlas doesn't behave like it's supposed to. If the jets were normal comet vents, their structure should be tied to rotation. And 3i Atlas rotates about once every 16 hours. In a typical comet, surface vents sweep around as the nucleus spins. Jets fan out into broader plumes, or pulse in brightness as they rotate in and out of sunlight. A single active vent often produces a heartbeat rhythm dim, bright, as the hot spot goes into shadow and returns to sun. But on 3i Atlas, the main jets remain narrow and sharply defined, almost laser-like, even as the nucleus rotates beneath them. They don't fan out the way you'd expect. They keep streaming, as if rotation barely matters. Photometric data backs up part of that story. Observers measure brightness changes of about 10 to 20%, locked to the 16-hour spin period. That modulation is real, but it's not the wild swing you'd expect if the jets were purely tied to rotating surface vents. The nucleus turns, the jets don't break up. They don't smear into wide plumes. They keep their structure. NASA's official line is that much of the brightness comes from the coma, a diffuse cloud that shouldn't care about the rotation of the solid core. Yet the brightness swings track the spin, hinting at coupling between jets and body that standard models struggle to explain. Comet dynamics expert Dr. Karen Meach has pointed out that even in highly active comets, rotation usually leaves a clear imprint on jet structure. If you see collimated jets that don't behave the way rotating vents should, you have to ask if something else is maintaining their direction. Something like a persistent internal mechanism, something deeper than surface ice. Now here's where the story gets messy on Earth, because this debate isn't just in the sky, it's also in publishing. Avi Loeb's group has spent months assembling the numbers behind the mass loss, the jet collimation, and the NGA puzzle. Their findings aren't hidden. They've submitted detailed manuscripts to respected astronomy journals laying out the contradictions, and repeatedly, the response has been declined before peer review. In some cases dismissed with a single sentence comparing the hypothesis to stories about fairies or ghosts. No technical rebuttal, no critique, just a closed door. That reluctance isn't random. Extraordinary claims face a higher bar, and astronomy has a history of false alarms that made the field cautious. But when caution turns into silence, it creates a vacuum. Real anomalies remain unaddressed, and rumor rushes in to fill the gap. Which brings us to the moment that could stop the arguing. A test in the sky. A gravitational checkpoint that doesn't care about anyone's feelings. On March 16, 2026, 3i Atlas is projected to pass within roughly 53.1 million kilometers of Jupiter, just inside Jupiter's Hill radius. That's the invisible boundary where Jupiter's gravity effectively overtakes the Sun's influence. The Hill radius is about 53.445 million kilometers. The margin here is razor thin. Less than 1% separates the projected closest approach from the edge of the Hill sphere. That region is basically the solar system's gravitational parking zone, Spacecraft engineers love it because probes can linger there with reduced solar pull. For an interstellar object on a hyperbolic escape trajectory, threading that needle by pure chance feels unlikely. And here's the key. As 3I Atlas approaches that boundary, the gravitational tug-of-war peaks. If it dips inside the hill radius even briefly, Jupiter could measurably alter its course. That change would be visible in the sky, and it becomes a direct empirical test, especially for any hypothesis that requires extra forces beyond the standard model. That's why the community is mobilizing. Amateur and professional networks are preparing to track the comet's position to the arc-second, time-tagged images. FITS files with Gaia-based WCS calibration, UTC synchronized logs, standardized submission checklists, all shared openly, all feeding into the Minor Planet Center. Because if the trajectory shifts, it won't be a claim. It'll be stamped into the public record by hundreds of independent measurements. Even missions like Juno, JUICE, and ground-based telescopes stand ready to record the encounter. Overlays, trajectories, hill-sphere graphics, already being updated in real time by the global campaign. This is how science tests extraordinary ideas. Watch the sky collect the data. Let the numbers decide what is possible. So here's where we are. In 18 days, we get a closer pass. Better geometry, better resolution, better constraints. In March 2026, we get a gravitational test with Jupiter that could lock in a measurable trajectory change. And between now and then, we're watching an interstellar object that shows structures that don't behave like they should, implies mass loss budgets that don't close cleanly, and produces jet behavior that doesn't map neatly onto the standard playbook. It might all resolve into something natural, a rare geometry trick, unusual dust physics, a weird but explainable nucleus. That's totally possible. But the reason people can't stop watching is simple. The anomalies are checkable, the windows are time-sensitive, and the next dataset could either shrink the mystery or force a whole new set of questions. And that's the tease for the next video. I'm going to break down exactly what to look for in the upcoming images and spectra, the specific signatures that would support normal comet physics, and the signatures that would make that explanation collapse. So if you want that checklist as soon as it's ready, subscribe. In Cosmos, we trust.